Hi, this video is a part of Machine Learning from Scratch playlist. In this playlist, I explain different machine learning algorithms implemented from scratch using Python. You can download the relevant Python files from the link given in the description of each video. Note that I do not code along, rather I make use of pen for explaining the tricky parts of code so that you people can read the notebooks and understand them yourself and of course re-implement them yourself. I'm expecting my audience to be well versed with machine learning general understanding and they just need little hints for implementation of these algorithms from scratch. In this video, I'll be talking about approximate nearest neighbor search algorithm, which is also called locality sensitive hashing. Locality sensitive hashing is more robust than KD trees. It can deal higher dimension and larger dimensions very well. How does locality sensitive hashing basically works? Let's jump to the whiteboard and notebook for understanding it in detail. We are dealing here with locality sensitive hashing algorithm, which is approximate nearest neighbor search. Why do we need locality sensitive hashing? Because nearest neighbors algorithm is computationally very expensive when it comes to testing given millions of training samples. Why? Because for each of the test point we have to calculate the distance from all of the neighbors, all of the training points, and retrieve the top 10 or top 20 neighbors, top 20 closest neighbors, and then what we do is then we use those samples for further calculations. Now the problem here is for each of the test point at query time, calculation of all these distances from the neighboring samples is really expensive and infeasible when it comes to real time calculations, real time predictions during deployment in different businesses. So what we do is we want to find out a way out. So what the idea is that let's divide this input space, consider this x-axis and y-axis, so we have this input space in 2 dimensions. So this whole space is what we call input space. The idea is that divide this input space randomly into different bins by drawing different lines. If we are dealing in 2D data, if we are dealing in 3D data, then we will be drawing plane, or if we are dealing with 4D or 5D data, so then we will be drawing hyperplane. I guess you got the idea what I wanted to say. So why this is line? Because we are dealing with 2D data, so to divide space into 2-dimension input space we need lines, but for 3D we need planes, and in higher dimensions we need hyperplanes. Okay, so the main idea is to divide this input space. And how do we divide it? By randomly drawing lines. Okay, so once we divide it, then we assign each of the data point a bin number. Consider this first line, this is the second line, this is the third line. So what we do is for each of the test point, we take a dot product of this test point with this line, and we look at the value. If the value is greater than 0, then it means that this data point is lying inside this first bin. If it is not greater than 0 and is less than 0, then it means it is not inside this first bin. Now what do I mean by first bin? First bin is actually this area. This whole area comes under the first bin, and this whole area is coming under the second bin, and this whole area is coming under the third bin, and this area is actually coming under no bin. So this is like 0 bin. So this is first bin, second bin, third bin, second bin, first bin, and 0 bin. So for each of the test point, for each of the data point, consider I'm looking at this data point. Suppose I'm looking at this data point. So what I'll do is I'll calculate this data point. I'll take a dot product of this data point with this line, first line, and then with this second line, and then with this third line. If the dot product between the first line and this single data point is positive, then I will assign this first data point this first bin. If it is less than 0, then I will look at the second line and the third line. In the same way it will go on. If it does not lie in any of the bin, so it means it is in the 0th bin. Okay, one more technical detail that we need to understand in this regard, that is each bin should be encoded in binary bits initially. So this 0th bin, so totally we have 3 bins, so we will need 3 bits. So this first bin will be basically 0 0 0. This 0th bin will be 0 0 0. This first bin will be equal to 0 0 1. This second bin will be equal to 0 1 0, and this third bin will be equal to 0 1 1. Okay, once we have encoded that, then what we will do is we will simply for each test point, we will check that in which bin this test point is actually occurring. And once we find out, suppose that is in the second bin, then we will retrieve all the samples that are occurring in this second bin, and then finally we will use those samples to calculate, to do the nearest neighbor weighting method, or whatever you want to do with the nearest neighbors for calculation. So these samples in the bin 2 will be used for the calculation of this test point. So this is very simple. We divide the input space So in a way, the more lines we have, the more finer, the more easier, computationally easier it will be, because the lesser sample point will be there in each of the bin. So for each of the test point, we will have to compute a smaller number of distances, pairwise distances. So but the approximation will be bad given we have very large number of random lines, because we are actually dividing the problem, dividing the input space so much that we are actually losing the nearest actual nearest neighbors information. So the whole process of locality sensitive hashing is finding out the balance between two. One, computational expensiveness of calculating the nearby neighborhood distances of nearby samples, and second one is accuracy, and they both are indirectly proportional. If we want accuracy, so consider we don't even we only want to draw single line, so we are dividing the whole data set into this first bin and second bin. The accuracy will be much better, except for samples in that area where there is uncertainty, where there will be issues, a bit issues, but largely the accuracy will be good. However, the problem is in the computational part. Here the computational part is still very expensive, so the computationally this algorithm will still work very expensively. Okay, what do we do then? We randomly increase different lines. So we will look at the effect of this computation and accuracy based on these random different number of lines in our notebook. We will explore this relationship, but generally this is the inverse relationship. We should know that. Okay, once we have this understanding, this basic understanding, then there is one more detail that to grasp, that is to convert these binary numbers into integers. Why do we do that? It's easier for calculation, and we'll be looking into that. Okay, so let me summarize what I have just said. First of all, we have to choose how many lines are random vectors that we want to draw. Then we find out the bin number for each of the data point by simply taking a dot product between data points and line, and if value is greater than 0, then assign the data point to that bin. Otherwise, do not assign that value to that bin. Then for convenience purposes, we convert bin number into integer format, and then for finding the neighbors, we retrieve the bin index, and the bin index will be in integer form, so that's why we convert it into integer form, these binary bits into integer form. We retrieve the bin index for a test sample, and we retrieve all samples inside that bin index, and we use them for our required task. And furthermore, the binary bits, the importance of binary bits is also that we could calculate for two different samples the similar binary bits. So if they are having more similar binary bits, it means they are more similar, two of the data points. Why? Because it means they are close by. How do we know that? Just let me go back and let me show you. Consider this bin index 2 and bin index 3. Both of these bin indexes are actually separated by each other by flipping just only single one bit. So this second one is encoded in 010, and the third one is encoded 011. If we convert this 1 to 0, so we are in the second bit, and if we convert this 0 to 1, we are in the third bit. So it means the difference between the bin number 2 and bin number 3 is only this single one bit. But for this bin number 3 and for bin number 0, we have the difference of 2 bits. So we have to change this first 0 and this second 0 to 1. Then we actually get the result of this third bin. So the difference between those data points which are occurring in this third bin and those data points which are occurring in this 0th bin is of 2 bits. So they are more far away from each other. So they are not similar. So looking at the bit number of each data point, if two data points are having minimum changes in their bit numbers, so it means they are nearby and they are more similar. So this is like comparing bits. We could also do this task of comparing bits. Okay, this was just because some people are interested in this kind of tasks, and this concept is also necessary for what I'm about to tell you, finding out the balance, which I have already explained, the finding out of the balance between computational efficiency and this accuracy. Suppose we have drawn 100 random lines. So of course, computationally, this algorithm will be very good, but the accuracy will be, of course, very bad. So another thing we could do is that instead of retrieving all these samples for test point in that same bin, we could also look at the bins very nearby. So we have this bin, we have a test point in this bin, so we retrieve all the training samples inside this bin. Now if we have some resources, computational resources, then what we could do is we could also retrieve the samples in the nearby bins which are only differing with 1 bit. So this means that we are also retrieving all the samples in this nearby bin and all the samples in this nearby bin. So in a way, we are improving the accuracy, and we are improving the classification or regression task that we want to do with this nearest neighbor regression or nearest neighbor classification algorithm. The accuracy or the error metric will be decreased. The accuracy will be increased doing this. However, the computational efficiency will again increase because we are including more number of neighboring samples, and we have to calculate more number of what we call pairwise distances. So the idea here is very simple, that instead of retrieving the same bin, we could also use the idea of retrieving the close by bins. And how do we find out the close by bins? By looking at the bits. If the bits are only differing by one number, so it means we are just looking at this adjacent bin. If it is if the bit is differing by two numbers, so we are looking at this adjacent and the adjacent of adjacent. So we have come to this area and to this area. So this is how we increase the search neighborhood distance and increase the accuracy by compromising and by utilizing some of the computational resources. Okay, now once we understand this idea, so this is what we will also encode. We will search also the nearby bins by differing 1 or 2 bits, and that for that what we will do is we will use the idea of combinations. And I hope so you know about combinations. So for example, we have to change bits in 3 different places. So then what we will do is we will create all the combinations, all the different combinations of these 3 different bits. So once we have all these combinations, then we flip the bits of query bin for all these bins, or for all these places that we have just generated using combinations, using different combinations. And we will look at the table. If that combination, or if that flipped bit is occurring in our table, then perfect, then we will retrieve the documents or retrieve the data points, because we are dealing with documents. That's why I'll be talking about documents in notebook, but generally I am here by document I mean data point. So we will be retrieving data point from those bins also if they are present in the table. So for each of the combination, we will flip the bit, we will look if they are present in the table. Once they are present, then we will retrieve those data points also, and we will use them also for calculation purposes. Okay, this is the whole idea. I hope so it makes sense. Let me jump to the notebook and quickly make you understand how it works. There are basically 2 main functions. One is for this general case, and another one is for searching the nearby bins. Once these 2 functions are clear, everything is clear, and these 2 functions are really easy once you understand this division of space into subspaces by randomly drawing these vectors or lines, and then for query point, just retrieving the bin number and retrieving all the simple samples in that bin number and using them for different calculations. And if you have understood the concept of comparing different bits and this bit number concept, if the bit number is differing by one number, then it is actually representing the associated bins, and they are nearby samples, and they are representing nearby samples. So using this idea, we have also talked about how we will retrieve the nearby bins and the nearby samples to increase the accuracy and compromise a bit of computational resources or computational expensiveness. Okay, let me go to the notebook for further explanation purposes. Okay, we begin by importing necessary libraries. This is a calculation of norm function for sparse metric, which we will be using. Okay, so we load the Wikipedia dataset, which contains different documents. So we want to find out the nearest neighbors or nearest documents to each other. Okay, this data frame is loaded by Theory So Theory is kind of a pandas and scikit-learn combined. Once we do that, then we pre-process this data set by adding this TF-IDF vector, by calculating this TF-IDF values for each of the document. This TF-IDF is in the form of dictionary. Then we extract this dictionary values and convert it and unpack it into separate features, where we are having value for each of the feature, and feature is actually the whole set of feature is actually what we call vocabulary size. So for each of the word, we will be having a TF-IDF value in each of the documents. So then what we will do is, this is a function to convert this data frame into a SciPy matrix, sparse matrix. This sparsity is in the documents. Usually documents are sparse because there are a lot of words which are not available, and there are very few words which are available in the document. So for a lot of words or for a lot of features, there will be value 0 stored. So for memory efficiency, we use these sparse matrices. Okay, then what we will do is, this is where our real code starts. So we train the locality sensitive hashing model by first randomly generating different vectors. So this is just testing this function of generating 3 vectors of dimension 5, and then what we will do is we will generate random vectors for the whole Wikipedia document, which is stored in this corpus. Okay, once we have done that, then we extract single sample, we take a dot product, and we look at the value with the first random vector, which is positive. So if it is positive, then we store the true value. If it is negative, then we store the false value. Then this thing is done for all of the vectors for the single sample. So this single sample, after calculating these values of all of these samples, then what we will do is not for single sample, this is where we are doing it for single sample, we will do it for all of the Wikipedia documents. Once we have done it, then the result is stored in the form of binary indices. This is like binary numbers. So this true means 1, this false means 0. So there are 16 numbers, and 16 numbers is kind of binary index of each of the bin. So what that means is that now we have to convert this binary index into integer. And how do we do it? It's very simple, as we know about it in our CS 101 class, as we have learned about it. This is like by the rule of binary number representation. What we will do is we will create this numpy single dimensional array. So these are different numbers that we have generated. Once we have generated these numbers, then we calculate the power of 2 for each of these numbers. So 2 power 1, 2 power 2, 2 power 3, 2 power 4, 5, 6, and this is done by this left shift operation. Then once we have done that, then we take a dot product between this sample and these random vectors. Now once we take that, then as I have already explained, so this line is already explained here. So this is just repetition of that line. But once we have that sample index bits, this is like binary representation, then we take this binary representation and take a dot product with the power of 2, and we get this single value, which is a decimal representation of this binary representation. Okay, now we have for each of the bin integer value, a single integer value. Okay, then what we'll do is we will combine all of the above logic into a single function where we are generating random vectors. We are taking a data and multiplying it with the random vector to get the binary representation of the bins. Then we convert this binary representation into integer bins, and then we use that integer bins to update table, so that table I is the list of document IDs with bin index equal to I. So this is like just storing the information for each of the index. Then at the end of this model, then we will retrieve this data and table, random vectors, bin indices, and bin indices bits. We don't need all of these, but still we will be storing this in the form of dictionary. Okay, so this model variable will contain this dictionary containing all of this information. There is another function, compare bits, as I've already explained, where we are just looking at the bits of two different binary representation of two different data points, and we just look at the bits which are same in both of them. If there are more bits same, so they are more close to each other. Okay, once we have done it, so this is just, we have taken two examples where we have taken the document for Barack Obama and Joe Biden, and then we looked at what we call the similarity by comparing the bits, and there are 15 number of agreed bits, so they both are really close to each other. Okay, then what we will do is we will inspect bins, and this is simply querying here we are looking how do we inspect bins, like we look at the similarity, but in this case we are looking at the cosine similarity. So we are looking at the cosine distance, basically, not similarity. Cosine similarity and distance is different. The difference is that in cosine distance, this length also, not only the degree, but the length also makes a difference of a vector, of a single vector. Okay, just have a look at it. What is the difference between cosine similarity and distance? This implementation is not actually all about it. It is just you can use any other distance also. You can also implement this whole thing for any other distance metric. Okay, once we have calculated the scores, then we take out the best items. Okay, once this is like something we have done million of times in our previous videos where we were talking about nearest neighbors. So this is like getting the similarity items. Okay, then this is just getting out these Barack Obama and looking at the document and the binary representation of that document, and then comparing it with the Joe Biden, as I have already explained, the number of bits, the number of agreed bits, and then this is just exploring what we have done till now. So if you look at it, so all of these lines are simply exploring and applying these functions. Okay, there is one part left that we have to complete, and that is querying this LSH model, locality sensitive hashing model, by searching even the nearby neighbors. And how do we do it? As I've already explained, we will make use of these combinations. So suppose we have search radius of 3, and again we are using 16 random vectors. So first of all, we will create these combinations, these different combinations. If we have understood this concept and these different combinations, then what we will do is in the nearby search bin, we have this candidate set initially, and for each of this different combination bits, for each of these different combination bits, what we will do is we will flip the bit of query bin, and then we will take a dot product with the power of 2 to get this integer number for the binary representation of the bin. Once we have that, then we will look at that bin number in the table. If that bin number exists in the table, then we will update our candidate set by also including the samples in those bins. If it is not if it does not exist in the table, then we go for the next combination, and next. Okay, once this function is also clear, then we have done our work. Then below that, this is just a query function where we have this model, and inside model, as I've already explained, we retrieve this dictionary containing data and table and random vectors. Using all of this, we will compute the bin indexes, or binary numbers, and using this candidate set, we will look at the using this initial candidate set that we have retrieved. Then what we will do is this nearby search bins. Using these nearby search bins, we will also update this candidate set by also retrieving those nearby bins samples, and using all of these samples, then we will calculate the pairwise distances, and then we will retrieve the top k distances from that nearest neighbors. Okay, now if we are done with all that, then below this line we are just looking at the effect, different effects and different compromises between computation and the accuracy. So as I've already explained, if we increase the nearby bin search, so it means we are looking at more and more neighbors. So of course computationally it will be expensive, but accuracy will increase. So this is these are the graphs. So the more search radius means looking at more and more samples. So if you are looking at more and more number of documents, then of course the query time will increase, but the cosine similarity will decrease. So in a way, the improvements, we will see the improvements in the accuracy. Again, if we look at the brute force query, where we are looking at all the distances, we can also find out the difference between the accuracies of both the approximate nearest neighbor using locality sensitive hashing and this basic nearest neighbor brute force search. Then you look at the effect of maximum radius. So this is how we do it, and by looking at this search radius, as I've already explained, the cosine similarity decreases and precision increases, and this query time increases, and the same goes for random vectors. If we increase the random vectors, then of course accuracy will decrease, time will decrease, and it will be computationally very efficient, but the accuracy will of course decrease. So the accuracy, the cosine distance as increases, so it means the accuracy decreases, and the accuracy or precision decreases, and the query time also of course decreases. Computationally it will be efficient, and the number of documents that we have to search will also decrease. I hope so this makes sense.